Hello and welcome to Positive Physics. Today we are looking at sound waves. Now the first thing to remember is that sound waves carry energy. We've all heard the story of the opera singer breaking the glass because they have found the resonant frequency. So we know that sound waves carry lots of energy. Now, if you want to find out a little bit more about that, do a Google search or look up the Tacoma Narrows Bridge, because that is an example of where the resonant frequency had drastic effects because the wind just blew at the wrong time. So have a look at that. But sound waves carry energy. Let's think about a trumpet and we'll think about how that transfer of energy occurs. So we have our trumpeter and they are blowing into the mouthpiece here. It passes through all the tubes and it will go through a different length of tube depending on which valve has been pressed down, and that will change the pitch of the note, and then it comes and passes out through the bell. Now as the trumpeter blows, because of the length of the tube, there will be a vibration set up in the air. And what happens is that vibration pushes some of the air particles closer together. So we end up with them squashed together. And in the process of those particles being pushed together, the ones next to them are pulled further apart. And the ones next to them are pushed together and then pulled further apart, pushed together, pulled further apart, pushed together. Do you get the idea? So we get these series of areas where the particles in the air have been compressed, they've been pushed together, and areas where they've been pulled apart. And we get what's called compressions and rarefactions. So if we think about what's actually going on, if you think about the air is moving down the tubes, the particles are all being vibrated in this direction. Okay, that is the direction of particle motion. And if we want to think about the direction that the energy is being transferred, well, hopefully it's coming from the trumpeter to the listener. So we've got this direction of energy transfer. So what do we notice? Our direction of particle motion, the vibration that we have here, is in the same direction as the direction of the energy transfer. So we have a specific type of wave and it is called a longitudinal wave. So just to remind you, longitudinal waves are the ones where the movement of particles or the oscillations are parallel to the direction of travel of the wave. So sound wave has this series of compressions and rarefactions. And you can see here we've got a loudspeaker and the sound is travelling to an ear. And here we have where the air particles are compressed together, and here the rarefaction where they've been pulled apart, and a series of compressions. But sometimes you'll see a trace like this on a CRO, a cathode ray oscilloscope, and you might see it in an exam question that you come across. But what's it showing us? Well, ultimately, it's showing us where those compressions are and those rarefactions. And what we can see is we have one complete oscillation is a full compression and a full rarefaction, and then we're back to starting again. So that's all those are showing. And on a cathode ray oscilloscope, the x-axis, so along here, will be time. So you can find out more information about your wave. So here we have a sound wave with a beautiful trace, but how would it look if the sound was louder? Well, let's think about it. If the sound was louder for the trumpeter, they would be putting more energy into that sound, but they would still have the same frequency. So all that's happening is that they are squashing those particles together more and pulling them apart more. And what that means is that the compression peak will be higher and the rarefaction peak, trough would be lower. So we're talking about amplitude. So remember this equilibrium position here is the equilibrium position for the wave. Here is the amplitude of the peak. Here is the amplitude of the trough. And what we've got going on in there is that you've got an increased amplitude up higher as we've got a louder, more energetic wave. Now, what about higher pitch? Well, the higher pitch means that there's more frequencies. Let's check this out. Put your hand in front of you on your throat, and if you make a note, like a hum, and then increase the pitch of that, you'll feel that the vibrations, there comes a point where you can't really feel them anymore, and that's because the frequency is such that your skin's not sensitive enough to be able to feel it through touch. And so what would that look like on this trace? Well, if pitch is related to frequency and this axis here is time, then if we've got a higher frequency, we know we're going to have more waves per second, which means that our trace will be squashed up. So it's as if you take this end and squash it into the other end and bunch everything up. Okay, and that would be a higher pitch. But what else can we get from these traces? Well, can we find the frequency of this sound? We've been told that this distance here on the oscilloscope trace is 27 ms. Now that's not meters seconds, that's milliseconds. So just be careful with these little prefixes here. Make sure you look out for them and substitute appropriately. So what's going on? Can we find out the frequency? Well, we've got one complete oscillation here. So all the way up, all the way down and back to the equilibrium position. Then we've got another complete oscillation. So now we've got two complete oscillations. And then we've got another complete oscillation. So we've got three complete oscillations in 27 milliseconds. So can we use that information? The answer is, of course, yes, otherwise I wouldn't have shown you. So let's think what we now know. 3 oscillations in 27 milliseconds means, and 27 milliseconds, remember, is 27 times 10 to the minus 3 seconds. Don't worry if you're doing a question and you're partway through your working. If you write down your value like this, I know it's not true standard form, you would change that to 2.7 times 10 to the minus 2, but you won't make as many mistakes if you keep it as 27 and just replace the prefix with the times 10 to the minus 3 for milli. Obviously it'd be times 10 to the minus 6 if it was micro, etc. So in the middle of your calculations, it's absolutely fine to keep the 27 as 27. So we know the time period, the time for one oscillation, is 27 times 10 to the minus 3 divided by 3, because we've got 3 complete oscillations. That's 9 times 10 to the minus 3 seconds. Frequency is 1 over the time period, so 1 divided by 9 times 10 to the minus 3, which is 110 Hertz. Can we now find the wavelength? Yes, we can. My apologies, Hertz are missing from there. Can we find the wavelength using the frequency? Well, we can, but we also need another piece of information, which is the speed of the sound in whatever medium this has been tested. And then we can use our wave equation, V equals F lambda. Hopefully that has been helpful.